In this session, we are going to derive an expression for rate of flow through Venturimeter. So let's consider a Venturimeter fitted in a horizontal pipe through which a fluid is flowing, and we are taking the fluid as water. Now we are selecting two sections, section 1 and section 2, for applying our Bernoulli's equation. Section 1 is selected at the inlet or the convergent portion of our Venturimeter, and section 2 is selected in the throat region. Now here the parameters at section 1 is denoted with the subscript 1. So D1 represents the diameter at section 1, P1 it is the pressure at section 1, V1 it is the velocity of fluid at section 1, and A1 it is the area at section 1. Now the parameters with the subscript 2 denotes the corresponding values at section 2, that is D2, P2, V2, A2 at section 2. Now we are going to apply our Bernoulli's equation at sections 1 and 2. On applying the Bernoulli's equation, we get it as P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. Now after writing the Bernoulli's equation, our aim is to somehow simplify our equation. Okay, we usually substitute whatever is known to us, or we make some assumptions, or we arrange our experiment in such a way that the terms or the variables, they get reduced. So here, since we have selected or we have assumed the Venturimeter to be fitted in a horizontal pipe, the datum heads Z1 and Z2 are at same level and they are equal. So Z1 and Z2, they cancel out from our Bernoulli's equation. So now the Bernoulli's equation simplifies to P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g, which can be rewritten as P1 minus P2 by rho g equal to V2 square by 2g minus V1 square by 2g. Now this P1 minus P2 by rho g is the difference of pressure head at section 1 and 2, which can be denoted by small h. So substituting the small h in your previous equation, we get it as h is equal to V2 square by 2g minus V1 square by 2g. Now the usual practice is that here we have our aim is to reduce the number of unknowns. So here we find that we have two velocities, V1 and V2. So always we try to express them in terms of, or we try to express any one of the velocity in terms of other. And this is done with the help of our continuity equation. Okay, so you know that continuity equation, when applied to section 1 and section 2, it goes like Q is equal to A1 V1 equal to A2 V2. Now you can write either V1 in terms of V2 or V2 in terms of V1. So here we are choosing V1 to be written in terms of V2. So V1 is equal to A2 V2 by A1. Now substitute for this V1 in our previous equation for H, that is in expression 6.6. So substituting that and simplifying and arranging your equation, you get V2 as A1 root 2gh by root of A1 square minus A2 square. So now we have got the V2, and we know that we are trying to derive an expression for rate of flow or discharge, and you know discharge Q is equal to AV. Here we have found out V2 and we are applying our continuity equation. So Q is equal to A2 V2. Now substitute for expression of V2 in this equation. And on substituting, you get your Q as A1 A2 root of 2GH by root of A1 square minus A2 square. And now the expression that we have got here for Q is known as the theoretical discharge. This is because we have derived that discharge based on the ideal conditions, on the ideal Bernoulli's equation. But we know that in actual practice or in actual situation, the actual discharge is much less than theoretical discharge, and that is compensated with a coefficient which is CD. Okay, it is known as coefficient of discharge or coefficient of Venturimeter, and such a discharge is known as actual discharge, and actual discharge is given by Q actual is equal to CD into A1 A2 root of 2GH by root of A1 square minus A2 square. So note that CD, it is coefficient of discharge. Since it's used here in Venturimeter, it is known as coefficient of Venturimeter, and always this value is less than 1. In case of Venturimeter, usually the CD value, it varies between 0.95 to 0.98. So students, note that most of the times you may not be provided with a value of CD. So it's very important you remember the range. You will have to know that it varies between 0.95 to 0.98. So assume suitable values within this range. And the value of CD is so high, which shows that the energy loss in Venturimeter is much less when compared to other devices like orifice meter, which measures the rate of flow. Okay, so thank you.